Hello everyone, this is RanadhirBharadwaj of EE278 Electrical Engineering. I would like to thank Professor Changchu for giving me these wonderful opportunities for explaining or presenting the final project term project is that is parameterizable LMS adaptive filter DSP IP core. Let's get into the project. Here we have the overview of the project introduction, architecture, implementation and verification, design and analysis, conclusion, appendix, references. Going into the introduction, let's find out what a filter is and what adaptive filter is, what are the types of adaptive filters, and what an LMS filter is. Going into the introduction, the usual method of estimating a signal corrupted by additive noise is to pass it through a filter that tends to suppress the noise while leaving the signal relatively unchanged. That is directive filtering. That is, whenever the signal plus noise is passed through a filter, it gives out a signal suppressing the noise. That is the filtering process, the regular filtering process. The design of such filters is the domain for optical filtering, which is originated by the pioneering work of Wiener and was extended and enhanced by Kalman, Bussey, and others. So that's the reason why we do have the filters called Kalman filters, Bussey filters, and so on. One of the most powerful as well as popular adaptive algorithms available in the literature is the stochastic gradient algorithm, also called the least mean square algorithm. Its attractiveness comes from the fact that it is very simple and robust. Let's get into the filters. Filters used for directive filtering can be either fixed or adaptive. Fixed filters. The design of fixed filters requires a prior knowledge of both the signal as well as the noise. That means we should have a knowledge of what the noise is actually and what the signal is actually. If we know the signal and noise beforehand, we can design a filter such that it should passes the frequencies contained in the signal and rejects the frequency band occupied by the noise so that we can get the complete pure signal or accurate in the signal. And the adaptive filters on the other have the ability to adjust their impulse responses to the filter out to the correlated signals in the input. They require little or no prior knowledge of the signal and noise characteristics as well. If the signal is narrowband and the noise broadband, which is usually the case, or vice versa, no prior information is not needed at all. Otherwise, they require a desired response or signal that is correlated in some sense to the signal to be estimated. Moreover, adaptive filters have the ability or capability of adaptability tracking the signal under non-stationary conditions. The introduction of LMS filter The LMS filter, adaptive filter, is the main component of many processing and communication systems, and traditionally, such adaptive filters are implemented in DSPs, digital signal processors. Their advantage include flexibility, programmability, reusability, and so on. But most of all, available of tens of hundreds of hardware multipliers available on the chip. Here we can see the block diagram of an LMS filter where X of n is an input, Y of n is an output, R of n is the reference signals, E of n is the error signal. Whenever the signal with the noise is passed through the filter, we will getting an output of Y of n with an error signal, which is again fed back to the input for the calculation and adaptation of coefficients with respect to the input again, so that there will be a sampling adaptation done, thereby increasing the accuracy of the signal output. The architecture, coming into the architecture, the basic architecture of the DFS core is called LMS adaptive filter engine, is shown in the figure, which is shown in the figure. Basic unit core consists of data memory, coefficient memory, LMS module, and the FIR module. The data and the coefficient memory may be implemented by RAM blocks. In particular, data memory is implemented as circular buffer, reducing memory traffic drastically when long taps are used, like for example 512, 1024, and so on. 2040, etc. are to be supported. Dual port memory is used in this architecture for coefficient memory, as each coefficient should be updated for new data. Here in the block diagram, basic architecture diagram, you can see the data RAM and the coefficient DB RAM. Going into the LMS filter and going into the FIR filter, generating an error. This is a basic architecture of LMS FIR filter where x of n is coming, x of j is coming, it's going and generating y of n, e of j as well, and generating the h of j coefficient, h of j, which are coefficients and which are fed back again to the input for the calculation adaptation. Then the implementation and verification of this LMS adaptive filter, it is done in both hardware and software as well. You can see the block diagram, the various approaches where the Simulink, which is in the MATLAB, which is done for the approximation and for the error checking whether it is converging to zero or not, and in the hardware language in the Verilog whether it's converging to the error signal, whether the error signal is converging into zero or not. Basically the different inputs are there for the different Simulink and the Verilog. For the Verilog the inputs and the desired are in the form of binary as well, but in the Simulink we give a dynamic input. The software implementation of the MATLAB, here you can see the block diagrams of adaptive filter, the Simulink model, and the coefficient update block diagram, how the coefficient is updated and the normalized as well. And the filter design which we had used is the Butterworth filter for the FIR process. In the Simulink model you can see the DSP, the input source is a sine wave, and the random source we are giving, which is given to the digital filter. Then they have gone through no adder and then have gone through the LMS filter, and thereby giving them to the time scope as well as a vector scope where it generates the frame rates and the frame, how the filtering is done and what the filtering shape looks like. And the time scope gives the error signal and the signal noise and the approximation of the input signal. And the block diagram of the updated coefficients, how the coefficients are updated, you can see in the block diagram and the right hand top corner. And next the filter design, as I said we had used the Butterworth filter. This is a dynamic simulation frame of an adaptive filtering. This goes on increasing as frame rate is increased. For example, the frame rate shown is 23569. As the frame rate goes on increasing, as it is a dynamic simulation, the frame rate goes on increasing and the filtering process continues forever. The simulation results of software in the MATLAB is shown. The initial simulation is of a signal, then the signal with low frequency noise, and then the signal which is approximated of the input signal. Then we can see the error signal which is converging to the zero, that is the adaptive filtering process as actually working. Then we are coming to the hardware filtering implementation. This is the second most step and the very crucial step to work out, rather than, because comparatively MATLAB is a very easy tool to work on and the Simulink model very easy to work on, but the hardware implementation takes a lot of time because we have to Verilog code and we have to pass the necessary parameterizable and randomizable and sources. The second step of the implementation was to build up a Verilog design for the application. As in the Simulink case, there are only two main functional blocks: LMS algorithm, the adaptive part, and the digital filter, the unknown part. The filter is implemented serially using a multiplier and an adder with the feedback as shown in the figure. You can see the figure. The hardware filter implementation, x of n and c of n were going through an adder, then multiplying, then one taps and giving an output. This is a simulation results of the hardware, which are where the error is converging to zero. This is our main aim, and I think we have achieved it in converging the error to zero. The first one is the input source, and the second one is the output source, and the coefficients are shown here, and the error is shown, which is converging to zero. The stability of this LMS filter. The LMS is convergent in the mean square if and only if the step size parameter satisfy, that is, which is in between 0 and 2 by lambda max. Here the lambda is the largest of the eigenvalue of the correlation of the matrix of the input data. More practical test for stability is 0 is when the mu, the of step size parameter is in between 0 and 2 by input of the signal power. Larger values for step size increases the adaptation rate, faster adaptation increases residual mean squared error. The future work, need to check the same hardware level implementation on EOS2 processor for the performance and compatibility issues. Data memory is implemented as a circular buffer, etc. You can go on that. And the future work is also here. We has initially used the dual port memory, but we need to use the single port memory for the coefficient memory, as each coefficient should be updated for the new data with the configurable parameters for data with coefficient width, length, width, precision, and converging factor, and to work on the clock cycles for the optimization. Here you go. Regarding my biography, I'm RanadhirBharadwaj and Masters in Electrical Engineering at San Jose State. I have 3 years of experience in the automotive field, worked as a graduate engineer trainee. Mm. Work done on source simulation and verification of immobilizer ECU, implementation of design specifications, control logic simulation. Uh, Thank you for your attention. Thank you for providing me this wonderful opportunity. Thank you very much.